This is the lecture 6 of thermodynamics. Okay, so in last class we have studied the relation. We solved this problem. Then we studied what is enthalpy, and then we uh, read the basic definitions and the basic equations of the enthalpy and its relation with the internal energy. Then we derived how it is related with the internal energy and with the heat. And then we studied the standard heat of formation. And these were the standard heat of formation values of some of the compounds. Okay, then I taught you that what are thermochemical equations. So thermochemical equations is a balanced equation that includes the enthalpy change. Okay. And these are the following conventions that has been adopted for these thermochemical equations. First one is that the coefficient in a balanced thermochemical equation refers to a number of moles, reactants, and products involved in the reaction. So the coefficients, okay, let's say this is our reaction. So let's say this is our reaction where getting converted into. So here A and B are reactants and your C and D are products. Okay, A and B are your reactants. C and D are your products. So what these values A, small b, small c and small d signifies. So these are nothing but the moles. Here A and B are the moles of reactants and your C and D are nothing but the number of moles of products. So how many moles of C is getting formed? How many moles of D is getting formed from this uh, A moles of A and B moles of B. Okay, so this is what here the small A, B, and C and D signifies. So here it is written that the coefficients, that means this small A, B, C, and D in a balanced thermochemical equation refers to number of moles of reactants. That means here A and B are number of moles of reactants and products involved in the reaction. And here C and D are the number of moles of the products, and these are involved in this reaction. The next one is that the enthalpy change of a reaction has to be specified with the appropriate sign and unit. Okay. So if delta HR is the enthalpy change of the reaction, let's say delta HR is the enthalpy change of this reaction. Okay, HR, enthalpy change of the reaction. Then if this is the case, then the sign of this delta HR, let's say it has a value of 81.4 kilojoule per mole. If this is the value, then we must assign a sign, whether it is positive value or it is a whether it is negative value. It is very important because I have told you in earlier classes that if these values are positive, that means the reaction is endothermic. Okay, if the value is positive, then that means the reaction is endothermic reaction, and if it is negative, then the reaction is exothermic reaction. So you must assign a proper sign to the value of this change of enthalpy change of the reaction. Okay, and also unit. Okay, so you must assign them accordingly. Third one is that when the chemical reaction is reversed, I mean if you reverse the chemical reaction, let's say this is your reaction. Okay, if delta HR was let's say for this reaction your delta H was 81.4 kilojoule per mole. Okay, now if we are reversing the reaction, let's say C moles of C, second, let's say C moles of C is and D moles of D are reacting together to give A moles of A and B moles of B. Okay, so this is the reverse reaction. Okay, this is nothing but the reverse reaction. So what will happen? The magnitude will remain same, but the sign will change. Okay, so if delta HR was HR is equal to 81.4 kilojoule per mole was the value in this case, then here your delta HR of this reaction will become minus of 81.4 kilojoule per mole. Okay, so this is very important. The sign will change, but the magnitude will remain same. Sign will change if we reverse the reaction. But magnitude will remain same. Will remain same. Okay. Okay. So now we have read all these 3 points. Let us move to the next point. Here they have mentioned that the physical states, that means gas, whether it is gas, liquid, aqueous or solid, of all species are important. Okay, and it must be specified in a thermochemical equation. Suppose you are writing an equation A plus B is giving C plus D, then you must write the number of moles. Okay, so let's say it was number of moles. Okay, and now you must specify in what states they are. Okay, let's say A and B were in gaseous state and C was in gaseous state but D was in liquid state. So you must assign all the physical states of all these species. Okay, so we specifying the physical states of all the species is very important. Okay, okay, so let us move to the next point. Okay, now we have, if the thermochemical equation is multiplied throughout by a number, let's say this was your equation reaction. Okay, now we are multiplying it with 2. Let's say we are multiplying this equation, thermochemical equation, with 2. So what will it become? So it will become 2 of A into A plus 2 of B into B to 2 of C into C plus 2 of D into D. Okay. So if delta HR was the enthalpy change for this reaction, then what will be the enthalpy change for this reaction? It will be nothing. Let's say delta HR dash is the enthalpy change for this reaction, then your delta HR dash will be nothing but 2 of delta HR. It will get multiplied by the number to which your equation has been multiplied. Okay, so what here is written is nothing but the if the thermochemical equation is multiplied throughout by a number, we have multiplied here with 2, then the enthalpy change is also multiplied by the same number. So your enthalpy change of this reaction is now delta HR dash, because your enthalpy change of this reaction will be different, and now it will be 2 times of what was the enthalpy change of this actual reaction. Okay, so if this was what we were taking 81.4 kilojoule per mole, then here in this case your delta HR dash will be 2 into 81.4 kilojoule per mole. This will give you 2 4 8 1 2 2 16 162.8 kilojoule per mole of enthalpy change for this reaction. Okay, so let us move to the next point now. Here the negative sign of delta HR indicates that the reaction is exothermic, and the positive sign of the enthalpy change of the reaction indicates an endothermic reaction. Okay, so I have already discussed this, that if your delta HR is if the value of your delta HR, that is enthalpy change for the reaction, is positive, then that means the reaction is endothermic reaction. And if your delta HR of the reaction, that is enthalpy change of the reaction, is negative, then it is an exothermic reaction. So, for example, these are the some of the reaction I have shown here. That this is the formation of water. Okay, so 2 moles of water is getting formed by reaction of 2 moles of hydrogen and 1 moles of oxygen, and this is the value of minus 967.4 kilojoule. Okay, so this is the value of the enthalpy change of the reaction, and here you can see that it is negative. That means if this is negative, then that means this reaction is an exothermic reaction. Now see here what they have done, they have reversed the reaction. Okay, now 2 moles of water is getting split into 2 moles of hydrogen and 1 mole of oxygen. Now once the reaction has been reversed, once the reaction has been reversed, the magnitude of your enthalpy change will remain same, but its sign will change. Okay, now if in this case it was negative of my 967.4 kilojoule, then it will become positive of 967.4 kilojoule. Okay, so here they have written that the standard enthalpy of the reaction, that is delta HR, which is not from standard enthalpy of formation delta H naught F. Okay. Okay, let me write it like this. Now it is your 1 second. So yes. So now if this was your exothermic reaction, so this is now your endothermic reaction, because your delta H is positive here. Okay. Here they have written that the standard enthalpy of reaction is nothing but the enthalpy change for a reaction when all the reactants and products are present in their standard. Okay. So if the enthalpy change of reaction is calculated when all the reactants and products are present in their standard state, then we will call it as the standard enthalpy of reaction. Okay. So and it is denoted by a superscript this to the symbol this delta H. Okay. So we will write it as delta H, what we write generally, and we will write this sign, okay, to denote the standard. So, and how we can calculate it? We can calculate it by the enthalpy of reaction under standard conditions from the values of standard enthalpies of formation of various reactant and products. So, if we are calculating it, the values, if we are calculating the values under standard condition, that means we are taking the standard enthalpy of formation of the reactants as well as the products. Then we can calculate the standard enthalpy of the reaction. Okay. So the standard enthalpy of reaction is equal to the difference between the standard enthalpy of formation of products and the standard enthalpy of formation of reactants. So this is very important, that the standard enthalpy of reaction is equal to the difference between the standard enthalpy of the products and the standard enthalpy of formation of the reactant. So here they have written that if we want to calculate the standard enthalpy of the reaction, then it is denoted by delta HR, and to denote standard we will use this sign. Okay, will be equal to nothing but the difference between standard enthalpy of formation of products. So what are the standard enthalpy of formation of products? Enthalpy of formation of standard, to denote standard we write it like this: product. So if why are using this sign? Because the products might be only we might get a single product, or we can also get 2, 3, 4 and more products. So we will take the sum of all these heat of formation of that. Okay, and the difference of heat of enthalpy of formation of reactant. Okay, so as we have taken the reaction, this was our general reaction, where we have taken A moles of A and B moles of B, and they react together to give C moles of C and D moles of D. Then what will be your delta standard enthalpy of reaction? That will be nothing but the summation of enthalpy of formation of products, that is enthalpy of formation of C and D. Okay, C and D, and minus the summation of enthalpy of formation of reactants. Reactants is nothing but A and B. Okay, so it will be nothing. It will become delta H naught F of C plus delta H naught F of D minus of enthalpy of formation of A and enthalpy of formation of B. Okay, now we have this. So enthalpy of formation of C will be nothing but the multiplying it with the number of moles and the value of its enthalpy of formation of C. Okay, and we have d moles of this C, and its enthalpy formation is this. Okay, now we have A moles of enthalpy of formation of A plus B moles of enthalpy of formation of B. Okay, so this is what we get as the standard enthalpy of your reaction. Okay, so this is your standard enthalpy of reaction, And why standard? Because we have taken the enthalpy of formation, the standard enthalpy of formation of the reactants and the products. Okay. So let us solve this problem where it is given that the standard enthalpies of formation of C2H5OH, that is ethanol, carbon dioxide and water, are minus 277, minus 393.5 and minus 285.5 kilojoule per mole. Okay, so we have provided with this standard enthalpy of formation of these species. Now they have asked that calculate the standard enthalpy change of the reaction. Okay, so now we have to calculate the standard enthalpy of the reaction. Standard enthalpy change of the reaction. So what is the reaction? The reaction is ethanol C2H5OH just we we can write it like this also, because we have to write their physical states. Okay, so we will have to move accordingly. So this is ethanol in liquid state. Okay, then it is getting reacted with 3 moles of oxygen, which is present in gaseous state, to give 2 moles of carbon dioxide, which is a gas, and 3 moles of water, is a liquid. Okay, they have written that the enthalpy of formation of oxygen in the standard state is 0. We have already studied it in the previous class. Okay, that the standard enthalpy of formation of this oxygen, hydrogen and nitrogen, these are all 0. Okay, so we don't need the enthalpy of formation of oxygen, the value, its value. Okay, so let us write what we are given, what we have given. So given delta H naught F of C2H5OH, what? Minus 277, okay, kilojoule per mole. Next, delta H naught F of CO2 is given, which is equal to minus 393.5 kilojoule per mole. And next, they have given delta H naught enthalpy of formation, standard enthalpy of formation of water as minus 285.5 kilojoule per mole. So in order to calculate, we will do nothing, but we will take the difference of enthalpy change of the formation of products and reactants. Okay. We know that delta H are not equal to delta H naught F of products and minus delta H naught F of reactants. So here we have, in products we have carbon dioxide and water. So we will take, so remember that we have to also take these number of moles in consideration. Okay, so we will multiply the standard enthalpy change, enthalpy of formation of CO2 with 2. Okay, 2 into standard heat enthalpy of formation of CO2. Okay, then plus 3 into, because here we are taking product side. Okay, we are taking the sum of product side. Okay, plus 3 into, what is the enthalpy of formation of water? This. Okay, delta H naught F of water. Now we will take it different with the reactant side. So in the reactant side, we have 1 mole of this ethanol. So multiplying it 1 with enthalpy of formation of ethanol. Okay, and then 3 moles of oxygen. So 3 into enthalpy of formation of oxygen. Okay, so this is what we have to calculate. Now let us put the values. Putting the values, we will get multiplying 2 with delta H naught F of CO2. So what is minus 393.5? Okay, now plus of 3 into delta H naught F of water is given minus 285.5. See, this is very easy. We just have to do the calculation, okay, and put the values. Now 1 into, so 1 is nothing. Let us just put the value of this enthalpy of formation of ethanol, which is minus 277. Okay, now we have plus 3 into enthalpy of formation of oxygen is nothing but 0. Okay, they have mentioned it over here that enthalpy of formation of oxygen is 0. So 3 into 0 will be 0. So this term will become 0. And this will become minus of 513 0 7. So this is what, if we multiply this, we will get this, and then plus minus will become minus, minus of 3 into 285.5 and minus of, so if this minus and this minus will become plus of 277 and then plus 0. So we will not write it. And if you solve this, you will get delta in standard enthalpy of formation of the reaction will be nothing but minus of 1366.5 kilojoule. Okay. So if you solve this, you will get this value for the standard enthalpy change of the reaction. So this is the answer. Okay. So what we have done here, we have just given this, already given with the values. We just have to uh, see what they have asked. They have asked the standard enthalpy change of reaction, which is nothing but the difference of the standard enthalpy of formation of products and reactants. Okay, so we have taken the difference of the products and reactants and heat formation, and then we put the values and then we calculated it and we got our answer. Let us move to the next problem now. Here, you see, they have again asked that we calculate the heat of formation for the reaction. Given that, we have to calculate heat enthalpy of reaction of this standard enthalpy of this reaction. Okay, sorry, we have to calculate the standard enthalpy change. Again, the same case of this reaction. So this is the same question as it was earlier. Here they have given that your carbon dioxide gas is getting reacted with this hydrogen gas to form a carbon monoxide gas and water. Okay, and they have given us the delta H naught F of CO2 as minus 393.5 kilojoule per mole. Next, we have given standard enthalpy of formation of carbon monoxide minus 111.31 kilojoule per mole and standard enthalpy of formation of water as minus 242 kilojoule per mole. So let us quickly calculate this. We know that we have provided with the standard enthalpy of formation of carbon dioxide, carbon monoxide, and water, because we know that standard enthalpy of formation of hydrogen is 0. Okay, so standard enthalpy of formation of hydrogen is 0. Okay, so now let us calculate. So the standard enthalpy change of the reaction will be equal to nothing but the difference of the heat of formation of products and enthalpy of formation of, sorry, I am mispronouncing that it is enthalpy over here, not heat. Okay, so the enthalpy of formation of reactants. So in product side we have, okay, let us first see if the equation is, this thermochemical equation is balanced or not. Okay, so this will be our first work to check whether the equation they have given is balanced or not. If it is not, then we will have to first balance it, then we can calculate the enthalpy change of the reactions. Okay, so here carbon is 1. Okay, so in product side we have 1 carbon. Here 2 oxygens. So 1 oxygen is here and 1 oxygen is here. So oxygen is also balanced. So we carbon and oxygen are balanced. Let us check the hydrogen. So here 2 hydrogens are there, and here in the product side we have 2 hydrogens. So this is a balanced thermochemical equation. Okay. So here they have given us a balanced equation. So we do not need to balance it. Balanced thermochemical equation. Okay. Now let us quickly solve this question. So here 1 moles of CO. So 1 into enthalpy of formation of CO plus 1 into enthalpy of formation of water, okay, in the product side. Now we will multiply it with the reactant side. Okay, so 1 into enthalpy of formation of CO2 and 1 into enthalpy of formation of hydrogen. Okay, so enthalpy of formation of carbon monoxide is minus 111.31, minus 111.31. Next, enthalpy of formation of water, minus 242 kilojoule per mole. Okay. Next, enthalpy of formation of carbon dioxide. So this is nothing but minus 393.5. And then we have, this is will become 0 because enthalpy of formation of hydrogen is 0. So we just have to calculate this even, and plus minus will become minus, minus of 242, and this minus minus will become plus of 393.5. Okay, so it will become, if we calculate this, what will it become? So let us add it. Okay, minus or minus minus will become plus, but we will have to again, it will again will become minus, the sign will become minus. Okay, so it will become plus 1 3 and plus 5 and plus 1 3. Okay, 353.31 plus 393.5. Okay, so let me just check it. 242. 53. Okay, this is right. Now if you plus minus, let us just, okay, I'll solve it for you. Now we have 393.5 minus of 353.31. Okay, so if we do this, then it will become 9 1 0 not 9, 5, that is 4. So if you solve this, you will get this value. Okay, let me just recheck it. That one, that is 19 and 93. That is okay. This is right. Okay, so this will be your answer. That means standard enthalpy change of this reaction. Okay, where your carbon dioxide is getting reacted with hydrogen and it is forming carbon monoxide and water. So this kind of question will be asked. So these are very easy. We just have to balance the equation and we have to see what values we have given. Like in this case, they all the values were given, and for hydrogen we know that, for oxygen we know that it is 0. So we have to remember that for the standard enthalpy of formation of this oxygen, hydrogen, and this nitrogen, they are 0. Okay, for because for diatomic gas it is 0. Okay, so otherwise we would not be able to solve this question. Okay, we will see. We will try to find what is the value of this oxygen. Okay. Okay, now we have solved this type of question. So let us move to the next slide. So here, what is heat of combustion? Combustion is basically burning. So the heat of combustion of a substance, if a substance is getting burned, is defined as the change in enthalpy of a system when 1 mole of a substance is completely burned in excess air or oxygen. If a substance is getting burned in air or oxygen, we are burning it in air or oxygen. Okay, then the change in enthalpy of the system, okay, the change in the enthalpy of the system will be heat of combustion. So when 1 mole of a substance is burnt in excess air or oxygen, then the change in enthalpy of the system will be called as the heat of combustion. It is denoted by THC, and here, for example, here I have taken this example that the combustion of methane, okay, in the presence of oxygen. Okay, so this is methane. CH4 is methane gas. Okay, it is getting burned in oxygen, and its combustion produces carbon dioxide gas and water. Okay, so burning of 1 mole of methanol in the presence of oxygen produces carbon dioxide and water. So what is the enthalpy change of the system now? Enthalpy change of the system they have calculated as minus 87.78 kilojoule per mole. If this is the case where the enthalpy change of the reaction is negative, what does it mean? That the combustion of methane is nothing but exothermic reaction. So combustion of methane is an exothermic reaction. Next, we have the combustion of carbon. So carbon is getting combusted into the presence of oxygen to form carbon dioxide gas. Here, the combustion enthalpy change is minus 394.55 kilojoule per mole. Again, this is negative. Okay. If this is negative, that means it is an exothermic reaction. C. Combustion reactions are always exothermic. Okay. So we will always get negative sign. Okay. So this is very important that the combustion reactions, that means if a substance is getting burned in the presence of air or oxygen, the reaction will always be an exothermic reaction. Hence, if the reaction is exothermic, then your delta S, that means your enthalpy change will always be negative. Okay, so combustion reactions are always exothermic reactions. Exothermic. Therefore, the values of their enthalpy change will also be negative. Okay, so this is what heat of combustion is. Okay. So before moving on to the next thing, that what are molar heat capacities and the relationship between them, let us first read what are extensive and intensive properties. Okay, so in thermodynamics, distinction is made between extensive and intensive properties. So what are extensive properties? So an extensive property is a property whose value depends on the quantity or size of matter present in the system. Quantity, that means you know the quantity, and the size. Okay, so quantity, it means if it is 1 kg or 2 kg. Size means it is 1 centimeter cube or 2 centimeter cube. Okay, so these are all the so the properties whose value depends on the quantity and size will be called as an extensive properties. For example, mass. Okay, so mass is a quantity. Okay, so it depends on the quantity, so it will be an extensive property. Volume. Volume is also an extensive property. See, by writing uh, these mass and volume and all these things as extensive properties, this means that we can add it or subtract it. Okay, so this is very important in a thermo. That means if we are solving a question, then we will be able to add it and subtract it. Okay. Similarly, internal energy, enthalpy, heat capacity, these are all extensive properties. Okay, we know that now that we already calculated that in the last class. I have told you that enthalpy is an extensive property. That means we were able to add it or subtract it. Like we calculated delta H, we calculated delta U. Okay, so if we can, delta H means what? S2 minus S1. That means we can calculate it. Okay, delta U is nothing but U2 minus U1. If you can calculate it, you can add it or subtract it, then it is definitely an extensive property. So basically they depends on the quantity. Okay. We know that delta H is enthalpy, is nothing but the heat content. Okay, heat content of a system. So if this is a system, okay, and let's say here heat content is H1, okay, and this is a system whose heat content is H2. Okay. If now if we add them both, let's say H2 is greater than H1. Okay. See, if we add them both, then the heat content of the system will now become H2 plus H1. Okay. Because here it was H1, here it was H2. Now if we add both, the heat content of the system will increase. That will become H2 plus H2. So that's why your enthalpy is also an extensive property. Similarly, internal energy, heat capacity, we will read in 2 minutes. These are all extensive properties. Next, we have intensive properties. So those properties which do not depend on the quantity or the size of the matter will be called as an intensity property. For example, temperature, density, pressure. So these are intensive properties. Okay, they do not depend on the quantity or the size of the matter. So these are all an intensive property. So the temperature, pressure, and the density. These are all an intensive property. So these questions are asked frequently in paper. So what are intensive and what are extensive properties? We basically have to choose which are intensive and which are extensive. Okay. So now it is written that the a molar property. Okay. Let's say chi m is the value of an extensive property. Okay. Let's say x is a property which is an extensive. Now if we take, okay, so x is an property which is an extensive. Okay. Now if we take it the molar value, like if we for 1 mole of substance, okay, if we take the value of x for 1 mole of substance, that means here now you are fixing, okay, the number of moles, okay, for 1 mole of substance. That means n is the amount of matter, and where now it is independent of the amount of matter. So here chi m, which is written as a chi by n, now this will be independent of the amount of matter. Okay, if this is the case, then this will become an intensive property. So let me clear. Okay, so this was an extensive property. Okay, and if we divide it with the number of moles, then it will become free from the independent of the amount of matter. Then what will it become? It will become, now it will not depend on the amount of matter, so it will become an intensive property. For example, molar volume. Okay, molar volume, which is denoted by Vm. Vm is nothing but V by N. Here we know that volume is an extensive property. If we divide it by N, if like we are taking volume per mole, then it will become independent of the amount of the matter. Then it will become your intensive property. So here your molar volume will become intensive property. Similarly, heat capacity was an here heat capacity was an extensive property. But if we are taking a molar heat capacity, then it will become an intensive property. Okay. So this is what you should remember, that if we are taking molar, then it will become from it. If it is extensive, then it will become an intensive property. Okay, so this was the basic of what is extensive and what is an intensive property. So concentration. What do you think? Concentration will be an extensive or intensive property? Concentration is an intensive property. Okay, let me explain you that. Let's say in this class you have an species whose concentration is 2 mole per liter. Okay, so now if we take some of the amount from this class and keep it in this, okay, so it will become, okay, so now what will be the concentration of the species in this class? It will not change, okay, because concentration is an intensive property. It does not change. Okay, so the concentration will remain same. If it, so here if it is not depending on the quantity, so it does not depend on the quantity, so it will be an intensive property. This implies concentration is an intensive property. Okay, now let us see temperature. So temperature, for this, let me take an example. Let's say we have a room. Okay, this is your room. Okay, so this is the room. Okay, its volume, initially its volume is V and pressure is P. Okay, so the pressure and volume is now fixed for this room. Let's say we divide this room in two parts. Okay, now if we are dividing it in this in two parts, then what will it become? It will become, now its volume will change. Here the volume of this room is now this. Okay, its volume is, let's say its volume is V1 and volume for this room will be now V2 because volume is getting changed. But do you think the pressure of the room will be changed? No, the pressure will remain the same. Or let's say, one second. What about the temperature? If initially the room temperature was, let's say, so let's say it was earlier 28 degrees Celsius. Okay, so now initially if it was 28 degrees Celsius, do you think the after dividing it in two parts, the temperature of both rooms will be different? No, the temperature will also remain same. So what we get, we will get change, pressure will remain same, and temperature is also remaining same. If it does not depend, so here what we are changing? We are changing the size. Okay, so if it does not depend, Then if it does not depend, then it becomes intensive. So here pressure and temperature are intensive properties, and volume is an extensive property. Okay, because by dividing it in two parts, its volume is getting changed. So if it is getting changed, then that means it is an extensive property. Similarly, boiling point. So let's say you have water in this glass. Okay, one second. Uh, so this is your beaker, and in this you have 100 ml water, and this is your 50 ml water. So let's say we'll just increase it. This is your 100 ml water, and this is your 50 ml water. So we know that boiling point of water is 100 degrees Celsius. Okay. So if we are reducing the quantity to half, so here water is 100 ml and here it is 50 ml. So the boiling point will remain same. The water will be boil at 100 degrees Celsius. So if it is remaining same and it is not depending on the quantity, that means not depending on the quantity, then it will be an intensive property. That means your boiling point is also an intensive property. Okay. Weight, of course, weight will be your extensive property. Volume, shown here that volume is also an extensive property. Length, okay. So initially this was your length of a tube. Okay, let us say this is your tube and its length is L. If we divide it in half, the length will change. Now its length is L1 and its length is L2. So if it is getting changed by dividing it into half, then it is an extensive property. Okay. So for today, this is it. So in today's class, we just read what are how a thermochemical equation is balanced and what and how can and how can we calculate these in standard enthalpy change for the reaction. Then we solved some problems, and then we read the heat of combustion, and finally the extensive and intensive property, and then we read the distinction between the extensive and intensive property. Okay, so this is it for this class. So in next class, what we will do, we will read what are heat capacities and what are molar heat capacities and their units and the relationships, and then we will solve some questions related to them. Okay, so that's it. I am ending this session for now. Thank you.